Hello, everybody. Welcome to today's session. Thank you very much for joining. This is the second part of a three-part series. This is our AI Engineering Bootcamp. And in this installment, we're going to be looking at the all-important step of scaling. So when you're moving from sort of pilot projects and initial investigations into scaling AI and rolling it out across your organization. Now, to explore this topic today, very pleased to have with us Brian Sather, who is the Director of Product Marketing at nTop. Hey, Brian, great to have you here. And we also have John Wild, who is our VP of Product here at SimScale. Great to have you too. My name is Alex Graham. I'm a Product Marketing Manager at SimScale. I will be here to moderate the session and guide the discussion and the Q&A at the end. So just before we get started, I just wanted to remind everybody, just like in the previous session, please drop your thoughts into the chat as we go along. You should have a chat and a Q&A panel in the GoToWebinar panel. Drop your questions in there as we go. We'll be looking at those as they come in, and if we have an opportunity, I'll also be putting those to the speakers during the session. We should also have time at the end to come back and have a look at the questions there as well. Okay, we're going to get started then. We can advance the slide. Here we go. So firstly, I just wanted to quickly recap what happened in the previous session. If you registered for that session, and of course this one, you should have an email with a link to watch that session on demand. Just to give you a quick overview of what we talked about, we had Armin from Convion with us, who was telling us all about a pilot project that he had run, designing a hydrogen ejector and doing a sort of deep design study and a parametric optimization using physics AI with SimScale. We also had Steve and Mike. So Steve was from SimScale, Mike from PTC, Onshape, which was the CAD software that Armin used in his pilot project. And so Steve and Mike then just kind of dug into the kind of supporting technology that we saw in the case study. So if that sounds interesting, please go and have a listen after this. But now we're going to move forward in our investigation. So we're going to have a think about the broader context and where engineering simulation processes can be accelerated and what that acceleration can do. So if we think about the typical process of an RFP response, generally once the RFP is received, then the new concept design is generated, and then there is a period of time before a simulation can actually be run on that design, which we refer to as the simulation lead time. It's all of that kind of CAD cleanup and setup and all of that work that has to happen before the solver actually starts running. Then we have the simulation cycle time, which is of course the computational part of the process, and then that can then result in a validated design. And typically in the time available, there's not much opportunity to investigate multiple different designs and different parameters and all of those trade-offs and sensitivities. Also, what you can notice here is that there are two key bottlenecks. There's the simulation lead time and there's the simulation cycle time. And what we looked at last time was an example of reducing that simulation cycle time using a physics AI model, which can then produce simulation predictions in a matter of seconds. So we can compress that part down and then explore a greater number of designs in that period of time. But the other thing to consider here is, I'm just going to move through the slide a bit faster this time. If we could actually collapse both of those bottlenecks, if we could eliminate both of those bottlenecks, so we take away the simulation lead time and we take away the simulation cycle time, that gives us enough opportunity to actually explore many, many designs in the same period of time. And we're kind of left with a single bottleneck at the end of the process, which is the validation. So it'd be a kind of a one-off or a few off validations of maybe a family of designs from which you can then select a final design. And so that's really the broader context, and what we plan to dig into today is how to get to this, how to achieve that reduction of the lead time and the cycle time. And so we're going to hear from Brian and John about that. So a very quick outline before we move forward. John is going to start with a quick refresher on physics AI and engineering AI. So these are two branches of AI technology which address the two bottlenecks that I was just talking about. We're going to have a think about running pilots and moving from those pilots towards full implementations, and what kinds of things to think about, what are the kind of typical tripping points and considerations. We're also going to look at how to power democratization using AI agents. And then we're going to hear from Brian about tackling that data bottleneck. So being able to produce data at scale in order to feed these models using fast, robust parametric modeling. So John, if you're ready to go, I will hand over to you.
All good? I think I've taken control and you should see my screen now. Perfect. Thank you very much, Alex. Brian, I realized while we're talking, I kind of got background envy. I thought I had a pretty decent background, like showing a bit about who I am and that I like stuff, bikes and things, but like yours is really distracting and really cool. So I'm envious.
We got the endurance back here. That's Shackleton shit. So yeah, that's a fun one, but I like the bike too.
I mean, me too, but now I want to swap it for a boat. So just so you know. Okay, so what we're going to do to start with is just run a quick refresher. So I think some of the team talked about this in the first session, but I think it's important to revisit just to make sure that we're all on the same page. So firstly, physics AI is the instantaneous prediction of physics. And for that, we generally need data. So Brian's going to dig into a lot of this later, showing you real workflows between nTop and SimScale. And hopefully you'll see a bit there too, but we need a lot of data. So we need to train a physics AI model, and that needs information. So we need simulation data that can come from you or it can come from us, but the model needs information. And that should describe a design space. We can give that information to the AI model so that when we give it what we call an unseen CAD model, so a CAD model that it has never seen before and wasn't part of the training data, it should be able to predict the performance of here, a pump, or an electronics box, or whatever we happen to want it to simulate for us. That's quite useful for a one-shot prediction, but it's more useful when we're looking at design optimization, because we can optimize throughout a design space using instantaneous steps to get to a really quick solution much faster. On the engineering AI side, I'll give you an example. Similar to what you shared, Alex, but not quite the same. So the example is that a request for a quotation or proposal comes into a company and an engineer has to handle that. Generally, they have to read through lots of documentation to try and understand what they need to deliver. What we are proposing they can do is ask an AI agent. The agent, using a large language model, can easily kind of go through all of the data that's required, and it knows what the output should be. It can run all of the simulations in the background, and it can produce really quickly a nice proposal. So there's still a human as part of this loop, but all of the menial work that happens on the right-hand side is taken away from them now. So they can do like the deep thinking, kind of harder kind of brain needed topics, right? And the AI can do the menial repetitive work. So the AI can understand the requirements. It knows what it needs to deliver at the end because it's seen a report before. It can produce a CAD model using an array of different parameterized models, and it can optimize the design to find the best one, and it can link that to the report. So that's like the difference of what these two things can do. So one is instantaneously predicting physics, and the other, I think, is more of a holistic workflow. And if we look at what Alex shared before with the whole design process, I would say that physics AI sits somewhere in the middle. So it's accelerating this optimization. And instead of having to run these simulations, the optimizer can just instantly get predictions and really quickly find the best design. And then engineering AI generally sits all the way across the top. So it could automate this whole workflow, or it could automate parts of it. And then if we compare them side by side, physics AI uses, at least in SimScale, it uses graph neural networks and physics-informed neural networks. There's many different models available, more are coming too. And on the right-hand side, we use LLMs. So here we don't need to train a model, but we're using models that we already all have access to control SimScale and to build holistic workflows on top of. So physics AI needs lots of training data. Engineering AI does not. We use the models that have already had billions invested in them to be trained, but we can layer customization on top to make these agents really good at specific tasks that we need them to run for us. And all of this can be deployed within our cloud platform. The advantage of that is it's behind the level of security that we provide. So even when we're using LLMs, the data still remains within our ecosystem. And it's a bit less risky than using an LLM that you'd find on the internet. And I would mention as well ownership. So any customers that train models on SimScale with physics AI, all of that is owned by our customers. So all of the data that you use for training and the models that you leverage and share within your organization, we don't see and cannot use any of that. And for engineering AI, obviously none of us own these models. We can use them, but all of our customers will own all of the customization they do on top. So if someone makes a model that's really good at understanding, for example, exhaust systems in cars, that will be your ownership and not ours. So with that, I've just talked holistically about engineering AI. We also have an engineering AI assistant. I'll show it in a second as a demo too, that sits inside SimScale. And this can help, if this sits alongside the designer or the engineer when they're working with SimScale. It isn't looking just at documentation. It runs way deeper and vertically. It can run things like designs of experiments. You can ask it to check your setup. You can ask it to just do the setup for you if you want to. You could make reports from it. So anything that's kind of a deeper simulation level topic, it can do for you. And it can also leverage traditional solvers, which there are many of in SimScale by now, or it can leverage physics AI for those instantaneous predictions as well. Engineering AI can also work holistically, like we said before. I talked about the RFQ automation, but maybe the second one is a good example around quality assurance and code compliance. So you might have a design that needs to meet lots of different codes. So generally we're ticking boxes, right, to make sure, yes, it meets this code, it's safe, it won't explode, it won't break under pressure, lots of different things. And what we could do is say, okay, here's my design, here are my codes, go and run all of the simulations that are needed to make sure that I meet my requirements. And so if we take this example here, it could run thermal simulations, frequency simulations, stress response simulations, all of the things it needs to say, yes, it meets requirements. And so now the engineer doesn't have to set all of that up anymore. They can just look at the results, validate that it matches the requirements, and then we're off to the races. Alex, Brian, feel free if you want to chip in and say anything, you are more than welcome to. Just saying that.
We had a question actually came in just while you were talking, which was just about clarifying the meaning of physics AI, that it's predicting whether it's predicting a 3D result or predicting a numerical value, like a pressure drop, like a single KPI. Which I thought was
okay, yeah, good question. It can do both. So you could, I'll show a heat exchanger example in a minute. It's the example that Brian will walk through. But with that model, I didn't actually do this, but I could have done. So I've had it set up to predict the 3D results. So it will show me the temperature or the pressure, but I could have said, give me the efficiency of the heat exchanger. So you could do either. You could get the real value that you need that you don't have to calculate, or you could just get the pretty pictures. Both, are totally valid. So it can do both. Does that answer the question?
Yeah, I think so. Thanks.
Okay, cool. Okay, so then we obviously have customers using both of these platforms now, and I think it would be interesting to share at least the experience that they've kind of gone through, going through the pilot phase, just testing it out, for a couple of days. Does it seem to give us what we need versus rolling it out to hundreds of engineers throughout an organization? And I've done it kind of side by side. So I think with physics AI, it's very easy to get started. Most of our customers have I mean, hundreds or thousands or more simulations already run inside SimScale, and they can easily grab that data, set up physics AI models so that next time they don't have to run simulations anymore. They can just do those instantaneous predictions, and it can be applied to any use case. And users can just self-serve everything online. So it's easy to get started, unless you don't have the data inside SimScale already, and you might need to bring in some third-party data. But again, for a proof of concept and a pilot, you might need 100 simulations or so, nothing like really crazy. And generally, it's quite easy to find that. So it's easy to find a use case that you can get started with. Engineering AI, I think, is even easier, and I'll again show it in a second, because it's already inside SimScale. We have an open beta program. If you'd like to test it, let us know. You're more than welcome to sign up, and we can share it with you. And it sits alongside engineers in the platform, and everyone already has access to it if they want to. If we want to set up these more holistic workflows, it might take a day or two to set up some kind of proof of concept, like a high-level automation, but we can do it. It's not really a problem. And I put challenges because I think this is important. It's not necessarily a challenge for us, but I think it's important with LLMs. I mentioned it before, but that the data stays within the SimScale ecosystem. So, I use LLMs all the time, especially when I'm making presentations, especially for the board and stuff. It's super useful to have like some kind of validation, but I have to be really careful what data I share. Using LLMs within SimScale, I feel more confident because I know that that data won't leave our ecosystem, right? It stays behind our wall, which is great. Then when we move to a full-scale rollout, things change a little bit, I think. We still have the same straightforward interface. It's still easy to set up and create these physics AI models. It's easy to work with first-party and third-party data. So that's like the easy stuff, but getting the data, the third-party data especially, is not normally so easy. So my kind of call to action, at least, and we talked about it before, but it's still super important, is to get ready and future-proof yourself now, because generally data is everywhere, especially simulation data. So now we're all using PLM, lots of CAD data is centralized. That's great. But simulation data is normally run by an expert on their machine, and it can be everywhere. So we really need to start centralizing and making sure that when we want that data, which we really will, we have good access to it. And it needs to be structured too. So it's really helpful at least to have tags so that we know that this belongs to this, or that these give a good pressure result or whatever, so that we know that when we want the results that we need, we can find them. I guess, Brian, you'll probably speak to this a bit as well, right? Because this is a challenge that we both understand.
Yeah, I think the structure, the availability of it, and then as your designs increase in complexity, how do you handle that as well? So for sure.
But I don't think I'm wrong in this. This is really happening, and I don't think we're going to go away from this. So future-proofing now is all we can do, right? We can't go back now.
I think that's whether it's, in terms of how you create your geometry, how you handle your simulation data, how you train these models. I mean, you're making an investment basically, and everything that you do right now is going to pay dividends as you go forward, because these physics AI models, it's an asset. Once you have it, it's something that you'll be able to use for the long term, and the sooner we can get them up and running, the better.
Cool, thanks. I agree. For engineering AI, I think a rollout here is also quite simple. The agents still exist in the workbench. What we find that users do, though, is start to layer on their customization on top. So they start to make agents that are really good at specific tasks. So you might give it prompts. So like, I'll take the exhaust system before, to say, we always want to know the pressure drop. We always want to know this. We're always interested in the temperature not exceeding some value. So it starts to know what you're trying to do. We can give it links to simulations we run before, or reference documentation, so that you've almost built now a car exhaust specialist agent. So there's some work to do there, but it's not really difficult. It's nowhere near like, I don't think, running with physics AI, because you're just giving it some customization layered on top. But I think the larger, kind of more holistic workflows, like the RFQ response, do need some additional work, but it's definitely possible. I think it's worth mentioning as well with LLMs, hallucinations. So everyone kind of talks about hallucinations, and that really means that an LLM can sometimes be wrong. I mean, humans can also sometimes be wrong, right? But I think it's also fine that LLMs are sometimes wrong. So if we've set up a model and an agent to go and do a workflow for us, it comes back with a result that isn't great, probably something went wrong, but it didn't cost us any time. And it's okay to say, like, go and do it again. And as long as we've got the human in the loop to validate that last design, I think it doesn't matter, because in the end, it will give us a great and a really nice step forward and an optimized model, something that we didn't think of or we didn't have before. And as long as we've got the human there to validate it, I think we're in good shape. I was a bit scared to use the word democratization, because 20 years ago, I was talking also about democratization in simulation, maybe longer than 20 years, but it was some time ago anyway. But I really think that simulation to a large degree has been democratized. So there are easy to use simulation tools. I think AI, though, brings another layer to that, because you don't even need to go to the tool anymore. Through a chat interface, you can ask for help and you can do simulation without even looking at CAD or simulation. So this is a whole other level I think we're now entering. So I think legitimately we can use the D word. I was just trying to think, are there other D words that you shouldn't say, but hopefully there aren't. I think I'm safe. I think I'm safe. Wasn't sure. So I'll just walk through a couple of things. So firstly, creating a physics AI model, and just to show how straightforward it is within SimScale. I apologize for some of this being grayed out. I've had to hide some customer data, but this is what we have within SimScale. So within your dashboard, it's easy to create a new model, to bring in data. So here I've used data that I didn't run, but somebody else has that I found from your heat exchanger again, Brian. And I can easily import that, ask SimScale to build a physics AI model for me, and then I can leverage it. So I'll show it in a second being leveraged just on one new CAD that hasn't been seen before. But like I said, this is really powerful when we start to run and leverage it for these optimization loops. So everything that happened on the right is all you need to do to create a physics AI model. So you just need to give it the data fundamentally, and choose the requirements that you want output. I should have chosen efficiency. I didn't do that. So I just get a pretty picture, but that's okay for this example, hopefully. So here now in SimScale, I can import a new model from Brian, so something that the AI has not seen before. I can use the physics AI model now to get an instant prediction. And I think, yeah, great. One time, it's kind of cool, right? It gives me an instant prediction, but again, we need to use it in these optimization loops. That's really the power. That's really like the accelerator, I think, that this really helps with. So anyway, on the right, at least now we can see, okay, this is how it's going to perform. I can see the temperature drop. I could look at the pressure drop as well. I could look at the efficiency. So I'm starting to get really useful information that could be fed back to the optimizer.
John, when you're training an AI model, generally how many different results are you looking to include to make sure that what it's giving back to you is accurate?
I think it really depends, but we're finding really 100 to 200 simulations starts to give you a nice baseline, but it depends how many variables you change. So I would say that's a good starting point, but it can be more. If we start changing many more variables, then yeah, we need to describe our 3D design space and kind of go through the extent of it quite nicely.
Yes.
But let me ask the same question back to you.
Same thing. Yeah, about 200 is what we have done before. Yeah.
Okay.
Also, it tallies pretty closely with what Armin shared in the last session.
Mm-hmm.
And he'd done a little sensitivity study on it as well. So he'd gone up to, I think, over 500 to see what the effect was.
Cool. Okay. Thanks. Okay, I'll just show a couple more things. So I'd like to show engineering AI working inside SimScale, and then also as a holistic workflow. So the idea here is that it sits alongside the engineer. So it can do different things, like I could ask it to check my simulation setup, investigate my results. I could ask it to do some design work for me. But what I thought is a really nice example actually is that we've got lots of different solvers in SimScale, tons of different commercial ones, and they all have different capabilities. So sometimes it's hard to go from one to another because the options aren't always the same between them. I thought that's a really nice example where we could use AI because it's such a time saver. So if I show you SimScale, so this is SimScale in the browser. This is some results on a table that I ran. So we're looking at stress. The areas that are red are high stress, and obviously the areas that are blue are low stress. So the AI actually set this up. I didn't do it. I have nothing to do with it apart from just simulate it. I can, but I didn't need to. But what I thought is interesting is if I go back to the CAD, so this was run under our new mark, so hexagon mark solver, but we have lots of different simulation types, and they're all really capable of different things. And what I could say to the AI agent now is simulate it with a static analysis type. So if I do that, what it should do, so this is the LLM now sitting inside SimScale. So this is our engineering AI agent over here on the right-hand side. I can ask it anything. I could ask it to check my setup or whatever I want. But I've asked it to set this up again with a static analysis type. So it will go away and it will create a new analysis type. It will port across everything it can do. So all the materials, boundary conditions, where it doesn't know what it's meant to do or it gets confused, it will ask questions. And then when it's fully set up the simulation, it will pause and say, all good, can I simulate it? And then you can say yes, and it will run. So far you can see, I won't stay for the whole thing, but at least you can see now it's set up the new static simulation type over here on the left-hand side. Then it will go through the materials. It's doing lots of checks to make sure it doesn't make mistakes. And then it will start to move the materials and the boundary conditions across. So this is something that might take, I don't know, it might take me 10 minutes, something like that to do manually. But now I don't have to. I can just ask it to do it. I can go and present a webinar, and I can come back and it's done and I'm up and running. So it saves so much time. I thought it was a nice kind of way to show how engineering AI can be used inside the platform. And then we can also leverage it for holistic workflows. I'll just show this, Brian, I think, and then I'll hand over to you soon too. So if we could build workflows that are more holistic, not within the workbench. So here, someone who doesn't know simulation and doesn't know CAD is asking an agent to do some design exploration. So this person is describing the CAD that they require. So they need a pin heatsink. This agent is very good at pin heat sinks, obviously. It's going to create those CAD models, make a project in SimScale, run a design exploration using the conditions that we're putting here. So different inlet temperatures, a heat load, and different power sources on the chip underneath the heatsink. And then it will go away and it will run an optimization. And it will show us the best design for cost, the best design for performance, and it will give us a nice report that kind of pulls it all together. And again, someone who doesn't know simulation couldn't do this. So someone needs to set this up in the first place. That's why I said it might take a day or two at the beginning, but once you've done this, simulation is democratized, right? Anyone can go and do this now. I think it's really interesting and really powerful. Okay, with that, actually, let me just check how the agent's doing. Sorry, Brian. Okay, it's nearly there. So it's setting up the boundary conditions because it's done the materials. Good. I'm just checking. Okay, with that, I'll stop. And right. I'll hand over to you, Brian.
Got it. Show my screen. Hopefully you'll see the presentation here.
Yes.
Awesome. Well, thank you, John. Appreciate it. And thank you, everyone, for joining today. I know we're all busy, so appreciate it. And thank you to the SimScale folks for inviting us to join this webinar on AI. Just a quick intro for everyone if you're not familiar with who nTop is. We do engineering design software. Specifically, we do computational design software. And we're really focused on how do we accelerate that requirements to design process. And we do that through kind of a novel approach towards really robust real-time parametric modeling. And our goal is how do we remove that barrier to optimization? How do we lower the cost of revision? And how do we just, just like John was saying, like how do we increase the speed of all those iterations that we do? Generally, what we find is that folks who use nTop are doing something that's highly engineered, and it just benefits from a lot of iteration. I think when we think about iteration, what we're really meaning is just like generating a lot of different variants of a given design concept. That comes through in a lot of like MDO examples, comes through in training physics AI, and it comes through in other applications like additive manufacturing and things like that. The main thing that I want to highlight is like we're not intending, as a modeling tool, parametric modeling tool, we're not intending to replace traditional CAD or CAE systems. CAD is a phenomenal tool at what it does for capturing design ideas, documenting them, creating all the information needed for manufacturing. And so like it's really a complement to what CAD does and really focus more on the front end of the design process. And kind of digging in on requirements to design a little bit, there's some fundamental challenges that we've identified in working with our customers in terms of what it takes to accelerate the overall design loop, if you will. And this is just a kind of a simple example of what we mean and where some of these bottlenecks come up. The first thing is capturing that initial design in CAD. We can do this pretty quickly. CAD's become super efficient. Where one of the bottlenecks comes up actually in creating our initial design is doing so in a highly flexible, highly parameterized way when we want to do a lot of design exploration. That tends to be incredibly difficult. And so just creating a really robust CAD file that allows for exploring the extents of our design space can sometimes be a challenge even for the most expert user. And then we want to go through this loop, right? We create our initial design, we test it using simulations, we determine whether or not our requirements have been met. If they haven't, which oftentimes they aren't the first time around, we kind of go through this, loop process where, we have a serial design evaluation process where we identify a new set of parameters that we want to test based off of what we learned from the initial analysis. We then make those updates in our CAD file. This often is a manual process. It can be automated to an extent, but oftentimes it means going through your model tree, going into your parameters dialog, and really just hoping nothing fails, right? We've all been victims to this when we go and make something that's more of a significant change than maybe we planned on at the beginning when we created our CAD model, and you start to see those little red exclamation points pop up, or all the different errors that might pop up at you as you go along. And we're left to diagnose our model tree and figure out where things went wrong and try and create a new update that we can run for this next iteration. And then simulation, just going through this process over and over and over again. We're thinking about traditional CAE with heavy mesh and model prep work that has to be done and long solve times because they're all run locally and things like that. It just becomes a burden, and it keeps us from being able to do this very, very quickly. And ultimately, we do want to get to a point where our requirements are met, but it just means going through this process over and over and over again until we reach that point. Now, one way, and John spoke about this really, really well, to accelerate it is through physics AI, right? By creating these surrogate models that we're able to evaluate the performance of new variants of a design very, very quickly. It accelerates that process significantly, which is huge. One of the overlooked aspects of this, though, we kind of talked about how many results we need to be able to have in order to train that model. Producing that data, if you have it as a something from previous projects and you've just got all this data that you've already created that you can feed in, that's fantastic. You're ahead of the game. You're already set and ready to go to do the training. A lot of times in the customers that we worked with, we need to create synthetic data that is representative of the type of design that we're trying to do, but it can be produced at scale upfront in the process. And doing this, just like we saw on the previous slide, it's basically the same thing, right? We need to produce a design variant, we produce the geometry. We need to then mesh, and we need to solve, And all of that can take days to weeks to go through hundreds of iterations to build that training data that we need to ultimately train the model. And so working with tools like SimScale, working with tools like nTop, our focus is on trying to minimize the amount of time it takes to generate that synthetic data so that we can train these physics AI models much, much faster and get them into use at a higher rate. And there's kind of like 3 core technologies. I'll hit on a couple of these within nTop that really I just want to kind of lay the foundation before we talk about what we're going to do to accelerate that process. The first one is implicit modeling. And this is, if you're not familiar with it, it's a kind of a fundamentally different way of generating 3D parametric geometry. It uses a sign distance field instead of the traditional BREP technology that you would find in your CAD software. It is really, I mean, the thing that sets it apart is you're creating essentially an algorithm instead of, working in CAD where you're trying to capture a singular design idea in many cases with a little bit of flexibility built into your parameters. You're creating an algorithm inside of nTop that's capable of producing any variant within the scope design space that you want to explore. And so it's really, really fast. It's very reliable in that you can't really break it, right? If it's something that you've scoped within the parameters, it will produce a valid geometry that you can move forward with. And it does leverage more modern compute hardware. It can, where we're often limited to high-speed single-core CPUs with our CAD software. This is something where we've parallelized it. It's got multi CPU or GPU processing and can run very, very fast to generate new design variants. The second pillar is this accelerated compute piece. And so we built everything for the GPU, for cloud infrastructure, for HPC. We do have GPU native algorithms in the software, including our lattice Boltzmann CFD solver. And really what this is about is just enabling more scalable design exploration. And in the context of physics AI, we're trying to enable more economical data generation so that we can produce the information and the data and the files that we need in order to train these physics AI models quickly. And so I'll skip the machine learning piece because that is the topic of the day. But that is the third pillar here is the machine learning integration. So this includes physics acceleration through techniques like pins and neural networks, as well as differentiable queries and inverse design. And so all of this is the technology foundation that enables what we're going to talk about in terms of more rapid requirements to design and just more of a fast loop through our design iterations. The other piece of this that is super, super important are these partnerships like what we have with SimScale. Being able to evaluate the geometry very, very quickly and having these integrations is critical. It's a long-standing bottleneck, right? If you use traditional CAE software, anytime you're moving between one application and another, it can grind your process to a halt, right? It involves multiple layers of translation. So in the case of nTop, you're converting an implicit model into a surface mesh, which then has to be meshed and then has to be prepped and solved in the simulation software. So any aspect of that we can eliminate one of those bottlenecks is huge. And that's what we've done with SimScale. So SimScale has actually gone ahead and built implicit interoperability directly inside of the software so that you can bring the file natively from nTop into SimScale, directly mesh it, and reduce the geometry prep from days to potentially minutes, and just move through this whole process of design exploration and synthetic data creation much, much faster. And what this all adds up to, right? If you look at these key technologies, the partnership, what we're trying to do is, again, move from requirements to design very, very quickly. And this is really centered on this middle portion of what you see in this graph, right? We want to go from requirements to having a final design and into production as quickly as we can, but the bulk of the time, right, is spent on this middle stage of iteration. And so what we're doing in nTop is we're creating a highly robust parametric model that allows you to represent any variant of this design within your design space almost instantly, which is huge. Then with our partnership with SimScale, we can analyze those designs very, very quickly to generate the synthetic data needed for training the physics AI model. And then once you have that, this process goes into warp speed, where we can now evaluate all of those design iterations even faster or near instantly, so that we can really power that optimization loop that much faster. And this slide really kind of lays out the process, right? We saw it earlier in the demo example, but again, we start here on the left-hand side where we're just building out the design space. And so again, like I mentioned, when we're using CAD, a lot of times what we're thinking about is capturing a design idea, parameterizing it where we can or where we think we might need to make small adjustments to the design as we kind of go through our validation and optimization process. With nTop, what we do is we essentially create an algorithm, like I said, that's capable of representing the entire design space, right? So we're not thinking about capturing a version of the design. We're trying to think about the extent of our design space and how do we model that very, very, very quickly. Then we conduct a design of experiments. We can use tools like nTop Automate and pair those with the simulation capabilities inside of SimScale to quickly generate the different design points. Again, we kind of talked about the number needed. We in different projects that we've had with customers try to aim for about 200 design points, and we can do that really, really quickly and without failure, which is nice. Then we go into the AI training, which is where we're importing that data into a tool like SimScale. And then that really is going to power kind of this inverse design process, which is possible, where we can start to say, hey, here's what our goal is. Here's what the different constraints are on the process, and go evaluate that and return, an optimal design that we can then generate the model of inside of nTop. Sorry, hang on one second. I'm sorry. There we go. So here's, example of what that looks like inside of nTop. And what we have here on the left is essentially that notebook that I was talking about. This is the algorithm for generating these different designs. In this case, we've set up custom blocks inside the notebook that are built to optimize different parameters. And so you can see this one is built for optimizing payload mass. We switched it here to an airplane. Sorry, this is the video that we had in time for the webinar today. For the next one, we have maximizing lift, but we do have constraints in here such as minimizing fuel mass and minimizing empty weight. And what it's doing is each time we hit play, it's evaluating we're calling that surrogate model to do things like maximize these different values, and then it's going to return the parameters that we need to generate the optimized geometry right within nTop. And so we can do that, like you said, we saw for range, we saw for payload mass, we can change the different objectives, we can change the constraints, and it's going to automatically do that based off of the optimizer that we've set up. And this is all calling a Python script here. And so all together, right, what we're trying to accomplish is just accelerating the process of inverse design. This is a summary of the overall process. We build that model inside of nTop. We do all of our training data synthesis with our simulation tool. Then we can power this optimization process in near real time. And we're just trying to really automate the optimization process, get much faster simulation. A key part of this too is just getting the robust design updates so that we're not constantly having to fiddle with the CAD software. And then, I don't know what I just did, sorry. And then being able to do, these parallel pre-computed different design evaluations as a result of having this physics AI model. So if this is something that we partnered with different clients on already, this is something that you're interested in doing, by all means, feel free to go to the nTop website. You can hit the get a demo button and punch in your information, and we will reach out. And we've done these types of projects with customers and gotten really, really good results so far. So if it's something that you're interested in, please reach out and let us know.
Awesome. Thanks very much, Brian.
Yes, I will stop showing my screen and change it over to you, Alex. All right.
Sure. I'm going to pop up one more slide. Lovely. Yeah, that was awesome. So I'm just going to bring it home with just one slide just to kind of sum up what we've heard, and then we're going to turn it over to the audience for questions. We've had some really good questions come in actually while we were talking. I think John and I have been answering some of them as we go, and we'll address the ones we haven't, and maybe we'll go over some of those other ones as well. So yeah, very quickly, we just wanted to sum up kind of what the key takeaways are, I think, from this session. So what to look out for scaling AI implementation across teams. So I've got here four sort of things to consider when it comes to making your AI journey a bit smoother. So we've heard a lot about data silos in this session. Of course, AI models need data, like any kind of AI model needs data. And so it needs ready and easy access to that data. So that's really a key consideration of getting your data kind of into the right form and into the right place so that you can actually do what you need to do with it. We also heard a lot about kind of the challenges of getting multiple tools to kind of work nicely together and to not kind of result in bottlenecks, I guess, when you have these processes, especially when we're trying to iterate quickly and many times around a workflow. You need to have really all of those bottlenecks eliminated wherever possible. So tool sprawl, it's definitely, it's real. And yeah, to generate that CAD at scale, just like you were saying, Brian, CAD robustness is often a challenge. I think nTop, you've got some really cool technology there. Yeah, it's like an alternative universe of CAD. It's very cool. Yeah, but anyway, so the interoperability and compatibility of tools in your tool chain is really important to whether you're going to really succeed or fail at this. I think trust is also like it's something which often crops up. There's obviously a need for validation. And John, you also mentioned like hallucinations. There are certainly some like tripping points to be managed with AI implementation. And I think that the way to really approach this is like transparency of processes, particularly like when it comes to having agents driving tools. Obviously, what they do has to be auditable and understandable by a human. And I think the nice thing about using an agent like in SimScale to do something like you were showing is that the agent is actually doing what a human would do in the software. So you can kind of go and review that. And by the way, I hope the agent is having a well-earned rest now. Did it finish what you were asking it to do there?
Yeah, it finished. It's very polite. It's
got a very positive mental attitude.
Your simulation is set up and validated. I've got a couple of minor warnings, but they don't prevent it from running. So it's kind of like it's integrated, right? It understands what it's done. So, and it's very transparent all the way. Somebody asked though, this is maybe a question to answer in the same sentence, right? They asked, does the agent tell you how it comes to each decision that it makes? And I guess we haven't exposed this information. We could do, but we haven't at the moment. So you can see what it is deciding between and what it decides, but not yet. We haven't yet exposed the decision-making process behind the scenes. I guess we could do though and leave it as optional.
So I guess we don't have that like show thinking drop down
feature
at the moment.
all
Yep.
good. Maybe
And I
some
guess you
beta,
can
right? So
ask it as
we can
well.
do
You can
anything.
say, you can also ask it questions about why it has made certain decisions
Yeah, yeah.
or what the alternatives are, and have that kind of like collaborative discussion.
Yep.
Yeah, and then finally, I think, well, as we were just talking about, the power of agents, it kind of opens the door to like a new means of integrating processes. So especially processes which are a little bit more fuzzy, which you can't really approach in the same way as we have done in the past with programmatic automation. So you can kind of go beyond what's possible there. Yeah, that's it for my summary. I think we have got a few minutes left, which we could use to have a look at some questions. I'm going to just leave this on the screen. Just a reminder for everybody, I think we now have about a 2-week gap before our final installment of the bootcamp series. That one is going to be, I think, quite focused on this like agentic AI. So yeah, looking forward to that. Please obviously come back and join us for that one too. So yeah, did you both have a chance to glance through the questions? I saw there was one here for you, Brian, which was crucial one. Is nTop running locally or in the cloud?
Yes, that's a nice easy one to start things off. So nTop does run locally. We are not a cloud software at the moment, and that's primarily just due to some of the clientele that we've got wanting to make sure they can run it behind their firewall. Not to say that cloud isn't possible with that, but they just prefer nTop sit behind in local on their desktops.
Makes sense. I had a related one actually. Is that can you then drive the processes that you were showing, the design space optimization, through like an API?
Yes. So we have. I mentioned it in one of the slides. It's called nTop Automate, which is our API into our automation tool inside of nTop, and so you can drive the whole workflow directly from that. And it also is the way that we can form integrations with other tools like SimScale, where we can automate how we pass data back and forth, and really just kind of streamline the process without a whole lot of manual intervention. And so not only can we do that directly with the CAE tools, but we can also connect to MDO tools if that's a desire, where it can kind of orchestrate the process between the geometry and all the different simulation tools that might be involved in the optimization process.
All right, and then I'm just glancing through to see kind of what we haven't already addressed. I saw there was a question.
Like Brian and I can probably both speak to this. It'd be interesting to see if we say the same. Somebody asked if they have a component that has, they gave 6 different factors that could change, like varying angles, fillets, height of fluid or height of load. So lots of different features. And the question was, how many, like, do we need to run a DOE with all of those different features changing to be able to train a physics AI model? You want me to answer that?
I would say you'd want to include the variables that you believe are going to have an impact on the resulting performance that you're interested in. And yes, you would want to run a DOE that kind of characterizes the extent of the design space that you'd be interested in exploring in the future.
Okay. Yeah, I would say the same. So you might, if you have 6 or 7, I think it was, and different features changing, you might need more than 200 simulations.
That's a lot. Yes.
It could be, right? It just depends. I mean, the amount of combinations then is probably, I don't know, millions or billions, right? It's really a lot. And so, yeah, you need to definitely, like a human, we also couldn't really guess, right? So you need to have some kind of experience of how different things impact the results. So yeah, I would say the same.
I guess you need to like draw the map first before you can then go and explore where you want to go in the design space. But if you're doing I guess one way that this could actually, that it overall could work out faster is because you could then run the simulations that form that DOE sort of largely concurrently. You could scale them out on the cloud. So you could get that mapping of the design space done faster than you would be able to do it if you were just doing a kind of piecewise optimization stepping through.
Or the structuring your data and understanding which training data you used for a given model is really important as well, because you do want to know, like, is what I'm feeding it as a test, like, is this new thing I'm giving it, does it fit within what I've trained the model on or not? Because if it falls outside of that, then you want to be more skeptical of the results. You can't train a model on a plane and have it simulate a car, right? So it's like you do have to make sure, like, you're in the bounds of what you trained it on, for sure.
Mm-hmm.
Yeah, I guess that's part of the data management piece, isn't it? Sort of keeping those links so you know what it's useful for. Yeah, I saw there was a question about, I'll just read the question out. While generating the data set, do we need to have models that have the same parameters predefined in those initial runs?
I think that was the one we tackled, correct?
I think it's kind of the same question.
This
yeah.
is unanswered. I think it's similar.
Yeah, I think I would say it's the same. Or
I was
similar.
wondering if they were asking like did they have to have exactly the same parameterization, which I guess they probably don't have to all have exactly the same, but they have to have enough commonality and be maybe using the same solver and have the same sort of inlets and outlets and topology, that sort of thing.
Not the same solver, because not the same solver, I would say. But as long as the data is still comparable, then yeah. But that's one thing that you don't need to adhere to, really. But yeah, it's mainly describing the design space. That's like the critical thing, I think.
Yeah, and I think some upfront work too, and making sure, like, the variables that you want to change, or the parameters you want to change, actually have some meaningful impact on the resulting performance. Is a worthwhile endeavor before you go off and conduct a six degree design of experiments, right? Like, that's a lot of work. So, like, confirming that those variables have an impact is definitely worth the time.
Yeah.
And then the same thing on different physics, right? It's like, just take the same thing. You can train it on different physics. You're just building out different physics AI models, and then you can orchestrate that via MDO or otherwise to do some additional optimization. But it's just kind of another angle, I guess, at that. It's just like, you can't train everything all at once. You have to do different physics separately and then compare it after the fact. You're just accelerating the process that you're doing normally.
Yeah. Yeah, I guess that also plays into we had some questions about, asking about can we predict individual KPIs, like I mentioned before, pressure drop as well as scalar fields, and so of course we can also train on even things like cut planes through the domain, but those it just that stuff has to be just defined and existing in all of the models in the training set, and then you can train it on anything that you like, essentially. So we actually went into some detail on this in the previous session. So Steve gave a little demo of how to train a model and how to select the different surfaces and scalars and everything. So if you're interested in that, then I would recommend reviewing. And actually, I'm just going to drop the link to the previous recording in the chat here, because somebody did mention that they didn't have the email. So there is a link to the recording. So anyone interested can just jump straight into that right now. Yeah, and that brings us, I think, to the top of the hour. So I think we're ready to say goodbye. Thank you very much to everybody who joined today. And thanks to Brian for joining us, and John for your great presentations. We look forward to seeing everybody for part 3.
Thank you, Alex. Thanks, John.
Thank you, Alex.
Thank you. Goodbye.